Here's video help for the last two problems in chapter 24. In 24.5, um, it, it's a short problem. Effectively, you're going to be looking at 1 over gamma g tau squared. And the question is, how can you make this smaller? And of course, then you want to make the denominator bigger. And so that your choice of g and your choice of tau follows from that. Your answer will be one of these three. In problem 24.7, you're adding two complex numbers. This is our general complex signal. We've got, partial volume effective. We've got part of it's from blood and part of it's from the tissue. And this is simply, when you're adding two complex numbers, it's like adding vectors, two-dimensional vectors. That's what the vector addition remark refers to. But you know what? Let's just look at this and simply say, suppose this thing's real, phi is 0. I've just got a real number here. And suppose this is big compared to that. Well, this guy can have its phase change whatever. It can change to pi. This can go negative and so forth. But it gets dominated by that. And therefore, the whole thing, suppose this was phi pi. This would be minus, this would be positive, but this is bigger. So this is a positive number here, and no complex part, and phi would be 0, and the phase here would not be indicative of the velocity-dependent blood phase. In part B, if we took our positive, bipolar, we have this velocity-dependent phase, and if we took the negative, of that gradient, we get a minus sign here. So in this, you're looking at the difference between those two. In part C, your phase due to an inhomogeneity doesn't care about the gradients. So what does that do for you in this whole procedure? Without my telling you anymore.